But then they moved to Georgia, so yeah, we had met down there for a while we did school, but yeah. I don't like that. Nope, nope. So you should always spicy me. I overslept and I'm here, so, you know, I made it.
Hi, Shelby.
Hey.
How are you?
Good, how are you?
Okay, thanks. Hi, Jake. Hi, Vanessa. Hi, Karen. Okay, we've got 8:30, so why don't we get started? Good morning, Psych Stats.
Good morning.
Welcome to Wednesday. Congratulations on a job well done on Monday. I thought that the journal club session went very well. Congratulations to Shelby on a very nice presentation. I was really happy to see all of that come together on Monday. I think it looked really good. And on Friday, we had a TED Ed session, and we were exchanging ideas about power and effect size and so forth, and we'll come back to that later on today. But I wanted to thank you also for your feedback on TED Ed. I found that to be very, very helpful. Again, I sent you an email on summarizing that. The greatest hits of the feedback had been that people generally like it, but they would benefit by having a couple more hours at night. So what I thought I would do is add the extra 3 hours as a grace period. We'll think of it that way. A little brief anecdote that you might find interesting. In one of my early years here, we had been in one of the classes, I think it was my PSYC 341 class, which is research in sensation and perception. And we were toggling around with some different software and so forth. We got a little bit behind schedule, but we were pretty much on schedule. And we had a big due date. The big project was due on a certain date. And some of the students said, we've been toggling around with the software. Can we have an extension? And I granted the extension. And there was like a round of applause when we granted the extension, right? And people were saying that. I heard people saying, Dr. Matthews is a genius. Dr. Matthews is the greatest person who ever lived. He granted us an extension. Okay. Then what had happened was I gave them a 2-day extension. And everybody was in this room plugging away on their report, like on midnight or 10 o'clock on the night before it was due. So even though the deadline had been extended, people just sort of, didn't work for those 2 days and then still raced for the deadline just like it was. And people were very angry. Gee, why did you extend the deadline? Because now I'm backed up with my other stuff. So what I think I'd like to do is extend this grace period. But I won't say that I'm really extending the deadline, so to speak. So I still want you to think about 9 p.m. as the cutoff. And if you haven't finished by 9 p.m., you're not going to be penalized yet. But I want you to have that be like a little alert that goes off inside of your brains that says, 9 p.m. it was due. I won't be penalized for the next 3 hours. But if we think about instead having the deadline at midnight, then you'll just say, I need to start until 11. I need to start till 11:30. Then you'll start thinking, I really would have benefited by 3 more hours. Okay, and this thing just keeps spiraling out of control. So I do like the idea of having a deadline with a grace period, and I do appreciate that some people have things that are going on at scheduled times in the early afternoon or the early evening. So hopefully by having a 9 p.m. due date, but also or deadline, but also a 3-hour extension, we can keep you aware of when things are really due without imposing any kind of penalty. Who's following that? Okay, all right. So that's how we'll think about that. It's due at 9, but you have a 3-hour extension. Okay, thank you for the feedback. I found that to be very helpful. Why don't we take a look at one other idea, and that is that it is important that if we are doing our TED-Ed lessons that we sleep after them before coming into class. We get a lot of consolidation inside of our brains when we're sleeping. And you don't need to look at any of these references, but in case you're curious, some people are very interested in how learning works. Here's a non-exhaustive list of some fairly recent articles that show the relationship between different kinds of learning and maybe different levels of sleep, REM versus slow wave sleep, this kind of thing. So you really are doing yourself a favor by doing the TED-Ed questions, then going to sleep, and then having to recall them again. It's what we might call retrieval practice. That's what people who study the process of learning would call this, and we want to spread our practice out. So I really appreciate that people have done a nice job of spreading out the responses over time using TED-Ed. And again, congratulations to the folks who had a really nice response to question 6 on Friday. I just provided feedback this morning on the question about how it is that we have a non-significant chi-square indicating a good fit to the model. And people generally did well with that. So we're spreading out our practice on questions like that. We're consolidating that practice through REM, an important principle for any kind of learning. Okay, well, speaking of that, we want to consolidate this information so that we can draw on it in the future. And in the very near future, we're going to have a quiz. As of tomorrow, we'll be having our quiz, and we'll take a little look at this. You've seen this before, so I won't spend a lot of time on this slide because it tells you about the context being low stakes, the format that you already know about, and it will be hands-on, as it typically is. This slide you've mostly seen before. This morning I added some of the items in red. Okay, and it looks like a lot, but I'm really just putting in some, I hope, helpful information. Let's drop down to the SPSS section just for a moment. This, by the way, is out on the S drive, so you can call this up at any time on the S drive. And you know that we've done correlations and regression. I had that the last time. What I can tell you is what you need to be able to do inside of SPSS, which we've already done several times, and some of you have done this in research methods as well, be able to use SPSS to determine the strength and the direction of a correlation, the proportion of variance explained, and we call that the coefficient of determination. That's the R-squared value, right? That comes out, right? And also be able to pull out a p-value. So what might happen is I might give you an exercise inside of Excel where you can use the equals Pearson command or the equals Carrel command, and you get the R value right there. But that wouldn't tell you whether it's statistically significant or not. I might say something like use SPSS now to figure out whether that's statistically significant. So you'd copy over that set of numbers, those two, and you plop them into SPSS, then click on Analyze and Correlate, you'd get out a sig value like we've done a couple of times. And that would tell you whether that correlation was significant or not, if it was less than 0.05. Who's okay with that? Does that sound familiar? We've done that once or twice here. Okay? So you can take advantage of SPSS to tell you about statistical significance, which is something that Excel doesn't do on the correlation statistic. So nothing really new there, but I just wanted to make that all explicit for you. When we're talking about in SPSS what kinds of things will we do with correlations. You can work on GSS93 files if you want to practice tonight. There'll probably be a GSS93 question there. You might be able to pull something out of Excel, plop it into SPSS, and figure out what's significant. Okay? Regression, just so we're all clear on that, be able to write a regression equation based on SPSS output. And you might remember that we have out on the S drive in our practice sets, we have a very simple PowerPoint file that tells you what to click on for regression. And then we have a whole bunch of different output boxes. You might just refresh your memory about what's where on the output boxes. So if you're writing the regression equation, I get my y equals mx plus b information from these different boxes, and this is all spelled out here. We've done this once or twice before, so we won't do it again this morning, but I just thought I'd give you a reminder of how you would be using SPSS to develop a regression equation. So I might have you work on a GSS93 file and then write on your sheet a regression equation. Remember that regression depends on what's on this axis and what's on that axis. That the correlation will be the same if you switch axes, but regression will be contingent on what's on which axis. Okay? At least that's true for raw score regression and not for z-score regression. Okay, so all that information is out on the S drive. Nothing particularly new there. I just thought I'd put in red down here for SPSS a little bit more detail about something we had already mentioned, correlation and regression on this. So nothing really new there, just a little bit more information. Okay? What we haven't done, and I've never done this with any group before, so you're my pilot group on this one. Usually in any given semester, probably 90% of the information is the same as it was in a recent semester, but I pilot 10% of things, or roughly. And so I thought I'd give a go at something that I really like to do on nonlinear regression. It's something called the solver, and we haven't worked on that yet. So I'd like to spend some minutes this morning, and we'll see if we get a question or two that we might be able to add to tomorrow's test. I do feel bad about having all this information. We only have 15 minutes tomorrow, so I really can't test you on everything. I'd like to figure out really how you're doing on all of those things, but we'll have time only to take a subset. So I can't guarantee that all of this will be on here, but I'll be looking at this when I make the quiz later today. Okay, so why don't we jump in and do some hands-on activities inside of something called the solver. And I'm going to ask you to open up a spreadsheet that I've never showed with a class before. This is the first time. It's called, out on the S drive, in the regression practice set. This is still on the topic of regression. Okay. It's called sinusoidal gas mileage regression. Okay? And these, by the way, are my actual gas mileage numbers for my vegan mobile. You might know that I've got a blue Prius that you see sometimes around campus, and it says Go Vegan on it. I mean, that's the vegan mobile. And I got the vegan mobile in August of 2009, and I do very diligently track my gas mileage. And interestingly, it follows a fairly complicated pattern, but there is a pattern there of gas mileage across these now, I guess that's 6 years that I've had the car. Right? So we'll just make sure everybody can call up this one. Again, it's in the resources folder. It's in the regression practice sets. Okay? How many people have found it? Okay, let me just go around the back and see if I get a C of sinusoidal mileage for the vegan mobile. Okay? All right, looks like everybody's there. Okay? All right, so very, very complicated stuff. There's way more information on this spreadsheet than we're going to need. So I'd like to highlight a couple of ideas that are of interest, I think, to all of us. And so first, we'll start out here in column B is the first one that's highlighted in yellow. I just have these different entries. Every time I'm running low on gas and I go into a gas station and fill up, I make a note of how many gallons I've added, and I make a note of how far I've traveled since then, and I compute my gas mileage. Who's following that? Okay? It might be that you do this yourself. It might be that your parents do this, or you have friends who do this. Not everybody is as freakishly interested in gas mileage as I am, but I think it's a really interesting phenomenon. I also note the date, so you can see August 28th is when I first had my fill-up, and then I think I have something as recently as, sometime fairly recently this semester. If you go all the way down, I have probably a couple of hundred entries here, okay? And those dates are not right, but anyway, 9/3. Okay, we'll leave those dates as they are. So sometime in September, okay, is when I filled up last. Okay? What I do is, interestingly, you might find this intuitive, you might not find this intuitive, is I actually convert the date into a cosine date. Okay? Who remembers hearing about cosines from trigonometry class, sines and cosines? Okay? So the idea is that as we are revolving around the sun, you can think of that as kind of like a big clock, right? And you can say that here we're at the maximally vertical point, and then down here at 6 o'clock we're at the lowest point on our vertical, and so forth. Here we're at the midpoint at 3 and 9, and so forth. So we're going around and around this clock, or we're going around and around the sun, and you can use cosines and sines to tell you where you are within a particular circle. Who remembers doing that in trigonometry or geometry class? Right? You can use cosines. So you can convert a given date into a cosine representation, and it's kind of like saying where are you in the 360 degrees of the clock. We can use a regular clock to tell us that it's now 20 minutes to 9. We can also express that time in a cosine value. Okay. You can say, for example, there are 24 hours in a day. If we start at 1 second after midnight, by the time we get to noon, we're half the way through the day. So it would be from up here, we'd be 180 degrees into our 360 degree cycle. Who's okay with that? Okay? So noon would be expressed as 180 degrees, or pi over 2 radians, if you're more familiar with thinking about radians. So you can do the same thing with a larger unit of time. Instead of a 24-hour cycle, it can be a 365.25 day cycle, the 0.25 accounting for the leap year, right, would be the way that you do that. Okay? So here's my actual date. Here's my cosine date. Okay? Here's my odometer reading. Okay? Here's the miles per gallon that I'm getting in a particular fill-up. And then over here, this is really what I want to call your attention to, is this graph. Okay, so here I have the date, and I have the miles per gallon at a given date. And so any given blue dot is me stopping at a gas station and reporting in my spreadsheet what my miles per gallon was for that particular tank full of gas. Okay? Who's following all of that? Is that working for us? Okay. And you might imagine that this thing just could have been completely flat. Like I always get 42 miles per gallon. I always get 38 miles per gallon, or whatever it is. But you might notice that it varies. And in regression, what we try to do is predict by having different kinds of models. And we spent a good portion of last week using first linear models, y equals mx plus b, but then we had a family of nonlinear models. Okay? Here's a nonlinear model because it isn't a straight line. Right? It's something other than that. And I hope you will agree that it's at least approximately cosinal, right, or cosinusoidal, whether it goes up and it goes down and it goes up and down. So hopefully people will see that. What I'd like to call your attention to is the number of parameters in this model. So if you'll join me by going up here, I'm now in cell N5. Okay? And it says something like my mean MPG, okay? And it's in green. How many people can find that cell? Is that working for us? Okay. That number I've got there is 42.7 and some change. Who can see that number? Still working? Okay. What I'd like you to do is work with me in a moment. We're going to change that number from 42 to 40, and we're going to see how this best fitting regression line, which happens to be sinusoidal, rather than a straight line or an exponential function or a logarithmic function or a quadratic function. Right? We're going to see how that sinusoid changes when we change each one of these parameters. Okay? So we're at 42. They're telling me basically that my average is 42. Can you join me in clicking in cell N5? And let's just turn that from a 42 to a 40. And then once you got it as a 40, hit enter, and you tell me what happens. I won't hit it here. You tell me what happens to the sinusoid. That red curvy line when you put in a 40. Okay, Vanessa's got it. It moves down, okay? Right? And hopefully people can see that. Okay, this is kind of like your y-intercept, right? Where do we center this thing? And we center it roughly at the mean. I'm going to do a Control-Z to bring that number back. I'll do a Control-Z. Does it come back to the 42.76? Yeah. Okay. Just for kicks, can we now change that from a 42.76 to a 50? Okay. Now the sinusoid goes way, way up. Okay. How many people get that? Is that working for us? Okay. Control-Z. So the idea, and what I like about this is it's a very simple kind of a model where we change this one and we see what happens on the graph. Okay. All right. One other thing I'm going to call your attention to before we start playing with some of the other parameters of this 4-parameter model. I have 4 parameters shown in green there. You might notice that I'm really taking a correlation with what the date is, and date is my predictor variable here, right? What the date is and what my miles per gallon is. And it might look like just a mess up there, but actually there is an R value that's significantly greater than 0. So if you'll join me now by clicking in cell R5, who sees that that's the R squared value? Does that work for us? Okay. It just turned out that the R squared happened to land in column R purely incidentally, and it's explaining about 36% of the variation. So this red line doesn't capture all of the variability. A lot of the dots are off of the red line, but it's explaining about almost 37% of the variability. 63% of the variability is not explained there. Who's following that? Is that working for us? Okay. Right. And so we're basically taking a correlation between date and between the model, I should say, and the data points, almost like the observed and the expected values. Right. The model is now going to be our expected value, and we're getting this kind of a fit. Let's go back one more time and take a look at the R squared. It's a 0.366. Why don't we change the 42 down to a 30 just for a moment? Okay. And then we can Control Z and bring that back. And we can Control Y. And we're toggling between 30, Control Z and Control Y, and 42. And what you might notice is that the sums of squares will change. The sums of squares is the next column over. We've computed this manually several times. Remember that sums of squares will be some score minus the mean quantity squared, and we sum all that stuff up. So if you now play around with something like the mean here, and you change that to a 40, you might notice that the sums of squares goes up to 4827. If I change that back, it comes down to 3350. Are people seeing that you're getting? Okay. So why is it that the sums of squares would go up when I put in a 40? Is it clear why that would happen? Well, I could put in a 50. Okay, let me put in a 50. Sum of squares goes up. Now the sums of squares, which is over here, is 13449. If I go back to putting it at that centered value, it's 3,350. If I put it in at 30, it goes up to 34,805. Okay? So why is it that the sums of squares is changing every time I change that value? Can somebody give us an intuition about that? Sum of squares? Sum of squared what's? What's being summed, what's being squared on the sum of squares? Either in this formula or any other time we've done sum of squares. You did it in research methods. You may have done it in Psych 100. What's being squared in the sum of squares? Sorry? Yeah, sum of the square deviates, right? Okay, deviates between what and what? The mean and the raw scores is one way to think about it. In the world of chi-squares, the deviation between the expected values and the observed values. But that's a recurring theme that Carl Pearson gave us, right? That we're looking at some model, some observation. That model might be a chi-square model. It might be a mean, okay? That model might be a sinusoid, okay? So as we move the sinusoid way away from the data, we're getting larger deviates. Does that make sense to us? Okay, yeah. So as we get larger deviates and we sum up all of those bigger deviates, we wind up with a bigger sum of squares. So one way of thinking about the best fitting line in any regression, it could be simple linear regression or more complicated regressions that are nonlinear, seemingly very complicated regressions like this, is we can always find the best fitting line by trying to minimize the sums of squares. Okay? What numbers can we put in here that gives us the smallest possible sums of squares? And that would tell us that we have a model that is at least the best fit. It might not be a great fit, but it's the best mathematical fit. As we put in other kinds of numbers, we get larger differences between an expected value and an observed value. Who's following that? Right? So one of the take-home messages, I think, from this course would be that regression is in part about finding the least squares model, is what it's sometimes called. We're going to try to minimize that SS. Does that work for us? Okay. So we're always trying to minimize the SS. And when you're finding the best fitting line in a simple y equals mx plus b equation, you've basically minimized the difference between your model and your observations. Okay, So why don't we try this now? We played around with the mean. I'm back at 42.7. Who's still there at 42.7? Is that working for us? Okay. Why don't we go over one more time? And this other thing says amplitude. Okay. And some of the folks who have S&P might recognize this, they might not. But if you did the TED Ed for today in S&P, you might notice that what we can change here is not just where is that curvy line centered, up, down, kind of like its y-intercept, but just how tall are the peaks relative to the troughs. Okay, that's the amplitude, top to bottom. So right now, we have a solution to this problem that's at 4.6. Can you join me by putting in, why don't we make it a little bit more peaky? We'll give it a higher high and a lower low. Can we go from 4.6 to, why don't we put in a 6? And hit, I'll hit enter. I'll let you hit enter, and we'll have you tell me how that sinusoid has changed when you put in a 6. And then you can control Z and get back to the 4 point something number. So how does that change things? Put in a 6. Keep your eye on the picture. Control that. So I'll go Control Y, Control Z. And if it helps, we can even make that a little bit more pronounced. I'll make it an 8. Versus back to here. Yeah, okay. So you can see that we're basically getting the peak to trough difference by changing that. Okay? And what you might notice is that we are, with a 4.6 amplitude, generating an SS of 3,350. If I change that up to 8 as my amplitude, I get a much larger sums of squares. Okay, so again, that parameter was used to help optimize the fit by minimizing the sum of squares. Okay? Who's following that? Who's not sure they're following that? Please let me know if you're not following that. Okay? So all these are set up to optimize this. Let's do another one. Okay? Maybe I'll go smaller on that too. So if I had just an amplitude of 2, now I have very, very low levels of peak to trough differences there. Okay, so we'll put that back to the original one. Okay, here's at phase. Phase is at 562, interestingly enough. Okay, if I change the phase down to, maybe I'll cut that value in half. I'll put it at 250. Right, you might notice how that changes. Right? Toggling back and forth, the relative position of the peaks and heights changes. Okay, this thing is now sliding over this way or sliding over that way. Who's following that? Okay, that phase manipulation. Okay, and then the last one is frequency. Okay, the frequency is really, really low at 0.0002. So that's almost like 0.000. It's 0.28, so it's almost 0.0003. So why don't I now double that and go to 0.0006? Keep your eye on the red line. Okay, and all of a sudden we get a much higher frequency. The peaks and troughs are coming more frequently per unit time. Okay, we can Control Z to get back to where we were. We can lower the frequency and put it at 0.0001. Okay, and that distorts that by quite a bit. Okay, so we have these 4 parameters that are controlling that. Who's okay with all of that? Yeah. Okay. All right, why don't we see if we can now use solver to get back to where we were. So let's just say that at some point, for some reason, I were playing around with this manually, and I thought that my best fit had been about 40 on the DC, okay, or the direct current, which is the mean of this. You might see us shooting a little bit low, but let's say that was my best guess. Okay? How can I take advantage of something called the solver to begin to optimize this? So here's where we're going to do something totally new now. We haven't done this before. I'd like you to, I'll demonstrate it up here once, and then I'll have you do it with me. You might notice that what I can do is click on a particular value like sums of squares, and I can try to minimize the sums of squares. I'm going to click on data. You can't do this yet, so just watch up here with me if you would. I'll click on solver. And inside of my solver, what I'm going to try to do is have an objective where I'm going to minimize that sums of squares and try to make that the smallest value I possibly can by changing these cells, cell N through Q. That's going to be my mean, my amplitude, my phase, and my frequency. If I can optimize those to try to minimize my sums of squares, maybe I'll get a better solution. Okay? So I'll click on solve. right? And it goes right back to the 42 where it was a moment ago, because 42 happens to be an optimal solution for this nonlinear equation. Okay? Who generally understood that work? Okay. So what's cool about this is you can kind of build your own equation. Excel comes with a handful of pre-built equations. There's one that's the natural log, exponential, quadratic, and different kinds of polynomials, and so forth, a linear equation, right? Those are some standards. But every once in a while, you might want to build your own equation. And because you're in an upper-level stats class, it might be the case that there could be an exercise where you would wind up playing with your own parameters and asking Excel to optimize this by minimizing the sums of squares. Okay, so why don't we try and do this together? So if you would join me by clicking on File, we're going to add the solver to your Excel spreadsheets. You'll click on the File menu, and then somewhere in there, there's an Options sub-menu. Options, I think, is all the way down on the bottom. Could you all click on Options? I'll do it with you. Okay, and you get this kind of a sub-menu that comes up. Do people get that sub-menu? Yeah, okay, that's there, okay. And we're going to click on Add-ins. Add-ins is almost all the way down. I'll point to it. We'll click on Add-ins. Okay, and you get a slightly different set of options. Okay, you wouldn't have to jot this down. If you needed this tomorrow, I would give it to you. Okay, and then we'll check the solver package. So let's see where solver is. Okay, maybe you can find solver, or maybe you need to go to Analysis Toolpack. Let's go to here. And add-ins here. Maybe you'll go to Go. Okay, and you might come to a package that looks like this, Analysis Toolpack, and really Solver is the main one that you want. So you click on those two and click OK. We'll see if I lost anybody there. And the check on all of this to see if we have it is if you go to Data, okay, you should have in your far right-hand corner the solver. How many people have the solver? I see several people. It looks like most of them. Okay. We didn't get it over here. Let's see if we've got that. Okay, so data, and we don't have solver. So I'm going to do real fast file options. Okay. Can you go to add-ins? Excel add-ins. Okay. Okay. If you could look on with Sarah just for now, we'll come back and get that. Okay. How many other folks got that and have the solver? Okay, most of us are there. Okay, all right. Why don't we try this? Can you join me in going? We'll start out with a simple one. We'll put it at 40. Okay, and we get some sums of squares that is going to be greater than the 3,350 that we had a moment ago. Sums of squares there is 4827 and some change. Okay. All right. Now what we're going to do is we'll click on the column S, row 5, that's the sums of squares, that's what we want to minimize. Okay. We'll click on Solver. How many people have that? Okay. And we're telling Solver, please minimize that cell by doing whatever you need to do to these other four parameters. Okay. Optimize those 4 parameters to minimize the sum of squares. We'll click on Solve. And it comes back with a menu that says, if you like the solution, click OK. And we'll like it at least for a moment. And it gives us that value. Okay. Who's following that? Who did something like this in research methods? Probably not. Okay, so it's a more complicated model, but you get the idea, right? And you can build. What I'm hoping to give you an intuition about is that you can make this model as complicated as you want. We won't do this today, but here's one other feature that I'm noticing. Look at the blue dots. Okay, you might notice that they kind of have sinusoids. By the way, anybody want to tell me what they see? What pattern do you see in the sinusoid? When is it high? When is it low? When is my mileage high? When is my mileage low? Across the years? Yeah. It's low in the winter, high in the summer, right? So after I did this for a bit of time, I hopped onto the internet and tried to figure out why is that the case. There are actually a lot of factors that affect any car's mileage, at least at this latitude. You can imagine if you lived at the equator, you don't really have seasons, right? So you wouldn't see this kind of a pattern. But there are factors that, maybe the engine is more efficient in warm weather than it is in cold weather. There are actually changes chemically to gasoline. They put certain kinds of I'll call it antifreeze in the gasoline during the winter so that your pipeline doesn't freeze. That's a good thing, but you lose a little bit in miles per gallon, and that's shown here. Also, typically, the colder weather deflates your tires a little bit, and the warmer weather inflates your tires a little bit. So that thing is cooking there, okay, right? So kind of interesting, right, that we get these fluctuations, and there they are. But there's some other pattern that you might see. When I had purchased my car, I had a set of data that looks like this on the left-hand side of the graph. Now here we are 6 years later, and I think that on average anyway, forgetting about a couple of stray points, the lows are lower than they used to be, right? So as my car is getting older, I think it's dipping a little bit. And so what you might want to do is if you had a best-fitting straight line, it wouldn't be probably perfectly flat. It would be probably tilted a little bit downward. Who's seeing that? Is that working for us? So I won't do it, but what I could do is I could add a linear parameter here and make it a 5-factor model and say, keep the sinusoid, but now grab that sinusoid and tilt it a little bit this way to get a slightly better fit, and that would probably even minimize the sums of squares further. Who's following that? That would probably work. It would be less parsimonious, but I would add one parameter, and I'm trying to fit here, I think I have 220 observations. Okay, so I'd be using 5 parameters to fit 220 data points. Not too bad. Pretty good ratio. Okay, so that's our introduction to the solver. The solver is something that we use for nonlinear equations to minimize the sums of squares, but just to find the best fitting line. And that's all we're doing in all of regression. The best fitting line might be remarkably complicated, but it's still the best fitting line. Okay? Who's all right with that? Yeah. It is good practice to understand something like the solver and nonlinear regression by looking at more than one example. So we'll take just a few minutes and look at another example. Could you close this one out? We're done with this one for today. Haven't figured out what test question I might ask about that, because I'm just introducing it now to you for the first time, but there could be something in there. Can we open up another one that people in my S&P course have not played with, but they've seen? I've put it up on the screen. We'll go to practice sets. We'll go to regression problems. And we'll go to localization acuity demo. So I'll make this really big, and I'll let you click on it, but it's called localization acuity demo. Okay. And we get something like this. And by show of hands, how many people find that? Is it working for us? Okay, localization. So here we have another kind of nonlinear fit. Okay, this is actually something of a simpler model. And let me set the stage just for a moment to let you know what's being measured here in this graph. So in one area of psychology, you might remember studying sensation and perception. In my sensation and perception class, we talk about lots of sensory phenomena, including your capacity to localize. So what I'll ask you to do is, contrary to what your mom's asked of you at one point, to never point. It's rude to point. I'll ask you to point at my nose right now, if you would. With your right index finger, can you all point at my nose? Okay, so everybody's pointing at me, contrary to what your mom's told you, okay? And if you now close your eyes and continue pointing to my nose, so all eyes are closed, okay? And now what you'll do is please continue to point to my nose as best you can with your eyes closed as I begin to move. Okay, so eyes closed. Okay, eyes closed, and I'll keep on talking. Right, so I'm now moving around the room. I'm off camera. I'm videotaping this, but people are following my voice. And what's interesting is every once in a while, I can even double back and sort of change direction. And somehow people, even with their eyes closed, are able to localize the sound. And if we wanted to, we could make real precise measures on how accurately you can localize my sound. Okay, so thank you. You can open your eyes. So that was fairly easy for you to do. It's one of the few things that newborn infants can do. Newborn infants, at the time of birth, assuming that they're full term, can typically localize. Right? Okay. We can measure how good you are at localizing, with what level of precision. Bats are freakishly good at this. Right? They can localize to fractions of a millimeter. Right? Okay. We can't localize that well, but we can localize reasonably well. And we can measure how well you're localizing by doing a simple test like this. I might say that this silver bar is at the 0 point on the window to door axis. And here I'm 1 unit toward the door, 2 units to the door, 3 units to the door, 4 units to the door. Here I'm 1 unit toward the window, 2, 3, 4, 5 units to the window. Who's following that? So what you can do in a simple psychology experiment is you tap here, and the participant has to respond, was that window side or door side? Okay, their eyes are closed. Right? I tap here, window side or door side, tap here, window side or door side, and we can figure out how their behavior is changing in the presence of this moving stimulus, and we can figure out their acuity in space. Who's following the idea? And what we'll try to do then is derive some kind of threshold. It might be the case that Gabby needs, 2 units of space, and Jake needs 2 units, but I need 4 units, and so forth. So we can measure our thresholds, and we can do that on a graph like this, where our x-axis goes from window side to door side, okay? And we're plotting the proportion of times that you say door side, okay? And as the stimulus gets more and more away from center and closer to the door, the proportion of door side responses will go up. As we get closer to the window, the proportion of door side responses goes way down. So we get some kind of a increasing function as we get increasingly toward the door and decreasing function as we move away from the door. Who's okay with that? Is that working for us? Okay. And then what we can do is fit a best fitting line, and it turns out for a wide range of sensory phenomena, the best fitting line is not a straight line, it's this sinusoid. It's actually kind of like a cumulative Gaussian. Who remembers doing the cumulative and non-cumulative Gaussians in TED Ed? Okay. You can actually use a cumulative Gaussian here. That would have worked just as well. We use something a little bit different. If you'll click with me, inside of cell H7, you might see the number 0.12399. It's a very, very faint gray. Okay. Anybody see that 0.12399? See that number? If you look up top, you will see the genotype that gave rise to that phenotype of 1.2. It's this crazy equation of 1 over 1 plus e to the k of f7 minus x naught. Right? I mean, it's a really complicated equation. Right? That's my nonlinear equation, and I can have Excel find the best fitting sigmoid, is what this thing is called, to fit the data. Okay? And interestingly, this takes just 2 parameters. So those 2 parameters are the slope of that, and where it's centered left and right. Okay, with the slope in the midpoint. So will you join me by clicking on C3? Okay, there is something that says slope, and in this particular equation, slope is captured by the letter K. It's at minus 0.5. Can you turn that to a 0 and hit enter? And you might notice now that this best fitting line has got a 0 slope. Who's with me on that? Okay, yeah, is that working for us? Okay, let's also now take the next one over. This is the midpoint, or x naught is how it's spelled there. Put a 0 in there. Okay, and what we're going to try to do is minimize the sums of squares by changing those 2 parameters. Where is this thing centered left, right? That's its midpoint. How steep is it? Okay, so we're back to a 2-parameter model, but it's highly nonlinear. Okay, we're going to have Excel find the best fitting line using solver. Okay. And we're going to, as always, try to minimize the sums of squares. We're using a least squares procedure to find the sums of squares. That's just a common thread in all of statistics. Okay? Okay, so hopefully your cursor now is in cell E3. We're going to try to minimize sums of squares. Can you click on data? And we'll see if you still have solver out there. It's going to be on your far right-hand side. Okay? We'll click on solver, and we'll take just a peek at solver for a moment. I'll slide it over. We're basically saying we want you to minimize cell E3, that's the sums of squares, make that difference between the observed and expected as small as you can. Okay? And we want you to do that by changing the slope, k, and x naught, which is this midpoint. Why don't you click on solve and have solver solve this nonlinear equation? Or look on with your neighbor if it didn't come up. Oh, okay. Right. Yep, there it is, right? Okay. I'll do it with you, and you might notice that this flat purple line all of a sudden hugs, to some extent, the data that it's trying to fit. Okay, there we go. Okay, and now that's the best fitting line by minimizing the sums of squares. And we have a bunch of values over here. Here I'm taking the R value between the observed values, which are shown in red, and the predicted values, which are shown in green. Okay, so that's a simpler model. It's only 2 parameters, okay? But it's not a straight line. Okay? I could have fit a cumulative Gaussian. Does anybody want to remind us what 2 parameters? It's a good practice question for tomorrow's quiz. What are the 2 parameters that go into a Gaussian curve? Whether the Gaussian curve is cumulative or non-cumulative. 2 parameters for a Gaussian curve. You've actually worked with each of these a fair amount, believe it or not. 2 parameters in the Gaussian curve. Here's a Gaussian. Here's another Gaussian. Do it again. Here's a Gaussian. Here's another Gaussian. How do those two differ from each other? There's that one. There's this one. They differ in standard deviation. Okay, so that's one of two parameters. Okay. Here's a Gaussian. Right? That's probably, like, your IQs are right about here. Here's my IQ. Okay. So how do those two differ from each other? The mean. Okay. So a mean and a standard deviation. Those are the two things that define any Gaussian. Okay. So I could have had, and by the way, really, really fat Gaussians that have big standard deviations, if you stretch them out, they're going to have really, really narrow slopes. Okay? If they've got really, really tight standard deviations, they're going to have really, really steep slopes here. And then they can be shifted left or right. Okay? So two parameters, just like y equals mx plus b, but they're different parameters than y equals mx plus b. Okay. Questions about the solver, a tool for finding solutions to nonlinear regression. Okay? That isn't canned, right? We get some canned solutions in SPSS or in Excel for quadratic equations and polynomials and so forth. But now you can build your own, okay? Of whatever complexity you like. I will not ask you to solve manually those problems tomorrow, right? But I might ask you to put in some data and use solver to find a solution. Okay, all right, very good. We have about 8 minutes left, and this is what I think I'd like to do. We did not get to fully go through the effect size and power questions from the other day. We went over a few of these, but we ran out of time on that Friday. Then Monday we had our journal club, and Shelby did her thing for the last 20 minutes of that session. So we didn't do all of these. And it's occurring to me that maybe some of them were challenging for you. Right? I think a few people commented in the response on TED-Ed that sometimes we don't go over some of the questions, TED-Ed questions that they were struggling with. So why don't I let you do this? Why don't I let you log on to your TED-Ed if you're so inclined, and maybe you can scroll through. We'll do it differently today. We'll let you scroll through the TED-Ed questions and see if any of them were questions you didn't really know the answer to. Right? I only spot check your answers and provide feedback on, like one, sometimes I do a double head or two of them. We go over some of them in class. I'm also projecting them up here. So I'll let you tell me what question you'd like to discuss. If there is, in fact, one, maybe this was entirely clear. But some folks indicated that they would benefit by going over particular questions. Yeah.
I'm just identifying a novel example of a small but...
Oh, love this question. Thank you. That's hard to do.
Yeah.
Okay? That's hard to do. Did you generate a response to that? I don't remember if you had a response.
I did, but I have no idea what I
Okay, all right, thank you. Thank you for being honest. And what I love about these questions, we can go right to the ones that, where people may have gotten stuck. I wonder if I can go to 10.2. I think I've got a slide here. And I might be on the wrong one. Small but reliable effects. I think I have a... Okay. I do recall from one of my slides, although I can't pull it up just at the moment, that my favorite example of a small but reliable effect is the discovery of Neptune. And I think I've got the planet right, but the idea was that people had been looking up into the skies for many, many years, and they figured out that there's this Venus that's really easy to see, and there's some other ones that are fairly easy to see. And somebody had discovered Uranus, a fairly large planet. What's interesting is that Uranus should have been at a particular point in its orbit. Here's the sun, okay? Uranus is going around in some kind of Newtonian ellipse, okay? And Uranus was supposed to be right here. And somebody took their telescope, and they were looking for Uranus, and Uranus wasn't right here. Uranus was, if you will, right here. A big so what? So so it's a little bit off, but it's probably measurement error. But then they looked the next night, and Uranus should have been there, or maybe one stroke over, and Uranus was here. So for a long period of time, generally speaking, Uranus followed the perfect Newtonian ellipse, right? So Newton basically got it right. But somehow, it wasn't just right. Okay? This was a very small effect, but it was reliable. It was not just off, it was always off in the same direction. And the fact that it was always off in the same direction suggests, according to Newtonian physics, that there must be some other body out here, which we now call planet Neptune, that has its own gravitational force and is systematically pulling this thing ever so slightly that way. The sun has much greater gravitational pull, so it's still going to be following its ellipse around the sun, but this thing is creating a very, very mild but reliable perturbation off of there. Okay? Wouldn't expect it to generate that, but that's actually how that planet was discovered. Somebody figured out, there's something not just wrong, but systematically wrong. And we can exploit that systematic deviation from this regression line, called an elliptical orbit. An elliptical orbit really is a regression line. Okay? It's not y equals mx plus b, but there is an equation for an ellipse. And they figured out we're off by that much. Let's take our telescopes, let's move out this direction and look for a planet that's this big or so big at a certain distance that would account for that departure. Who's following that? Okay? Pretty cool. Roulette wheel was another one of my examples, right? And a roulette wheel, you tell me, what are the colors on a roulette wheel? Red and black. And so you can go to a gambling casino and you can put your money down on red and black, and it's 50-50. So it's kind of uninteresting, right? You win half the time, you lose half the time. So how does the casino make its money on the red and black roulette wheel? One hint is it's looking for a small but reliable effect, okay, which is the theme of this question. Maybe we don't have gamblers here. I'm not much of a gambler, but there are two numbers out of like the 38 numbers. There's a green 0 and another green double 0. Has anybody ever seen that on a roulette wheel? And if you're betting red and black, the rule is you have to win, okay? So if you bet red and it comes up red, you win. Red, you're betting red, it comes up black, you lose. If it comes up green, you also lose if you're betting on red, okay? And so basically it's 50-50, but there's a small chance, like 1 out of 38, it will land on green. So their profit margin is essentially 1/38. Okay? That's another example of a small but reliable effect. Okay? We just had a wonderful presentation by Dr. Maureen Craig, who is a social psychologist. She was looking at implicit attitude issues and looking at all kinds of subtle implicit forms of discrimination. She kept on finding statistically significant effects in the ways that you might expect, that certain minorities were treated less favorably, as Dr. Bickman's article might suggest. It kept on coming up. She must have used 9 different samples. She always got it. Okay? She always got the significant. Never did that effect ever explain more than 4% of the variation, if you did an R-squared, and typically it was down at 1 or 2% of the variation. Right? So we were doing R's a moment ago in R-squared. Her R-squareds were, like 0.01 or 0.04. They were in the right? So the effect was always there. It was reliable, right? But it was never particularly large. On a scale that goes from 0 to 1, it never even cracked, 0.05. Does that help? Okay, right. I wouldn't expect you to be able to. So it's tough to be able to think of those numbers. Another one that Bill Clinton used to use a lot is something like a grocery store. Grocery stores make a little bit of money off of a large number of people, and so does Walmart. Okay, other kinds of organizations, probably like a car dealership, will sell many fewer cars in a given day than Walmart will sell units. Even if you just control for town, like how many units does a Walmart in Newark sell, and how many cars are sold in Newark? Okay? The number of cars is going to be much smaller, right? But you're going to get a much larger profit margin on any one of those cars. Okay? So the grocery store is got a very reliable effect. They know that you need food, and they're going to make just a little bit of money off of that need. There's going to be this very large base. They can count on that. Small effect size, but it will be there reliably. Okay. Something else. Do we have time for? We don't have time for one more. All right. Well, if you do have other questions, why don't you email me about the TED-Eds? The TED-Eds, again, will not be on tomorrow's exam, but they could play a role, I guess, how you think about Friday's essay, right? You're writing about what's of interest to you, and maybe you'll be able to adapt some of that information into your essays. Okay, so please practice what we said to practice for tomorrow. Here's the practice summary, and I look forward to seeing you tomorrow. So Vanessa, actually, you did get there on the solver, right?
Yes.
Okay.
Yeah.
Okay, I'm not sure what happened the first time, but it works the same way.
Yeah, it works.
Okay. All right, thanks.
Thank you.
Okay, see you.
Have a good rest of your night.
You too.